Today we are going over how to draw isomers. So just to review, an isomer is when you have the same chemical formula but a different structure and therefore different properties. It's the structure that causes the properties to be different. So students notoriously have trouble drawing isomers, so I'm going to take you through step by step. So the first isomer is always a freebie. So if you wanted to draw the three isomers of C5H12, the first one is always the straight chain alkane, and it would be C5H12. These are all going to be, when we're done, C5H12. All right, and this one would look like this once it has all its H's. Now, the model kit, it looks like that. So it's a little hard to see. I'll put it on there. So there's our model kit. It's 5 in a row. Don't worry about the fact that they kind of alternate like that. The way we look at it in 3 dimensions, they all look like they're in a line. So we kind of look at it and draw it like that. But in reality, they are kind of staggered. I'm not going to get into that. So a common mistake that I see is for the second isomer, someone says, well, how do we have a different structure? So you'll see students do stuff like this a lot. I'll use my notepad and I'll get this. They'll be like, okay, well, what if I did this? There's 4 in a row. Well, there's my 5th, okay? Well, that would be like drawing this. So if I drew it this way, hard to see, but if I have my 4 in a row and then I just point one down, that doesn't make it an isomer, because all I have to do is just twist it back and it's still a straight chain. You could even draw something like this. That is also a straight chain, because if you count them out, if it's not about their shape, it's about how they're connected. These are all connected in a line or in a sequence. So these that I just drew are the same as the first one. They're no different, okay? Even if you were to go even more extreme and draw it like this, and you'd say, well, that has to be different. Well, look, 1, 2, 3, 4, 5. I drew too many carbons, but if you connected them like that, we're ignoring H's. That's still the same molecule. It's just connected. I just bent it. I'm just doing this. All I'm doing is just moving it around. So like you could draw it like that, almost like a bowl. That's still connected in a straight line as far as we're concerned, because 1, 2, 3, 4, 5. In order to make a isomer, what you have to do is disconnect a molecule and reconnect it some other place. So the way we do that is by literally disconnecting a carbon and reconnecting it somewhere else that is not on the main chain. All right, so this is the first isomer. So if you look at it, it might be a little hard to see. Maybe it's like that's a better angle. So if you look at it, it kind of looks like this. This is how it would draw in 2 dimensions. It would be 4 in a row, and then I go 1 in, and there's my extra carbon. So now if I were to put in all my H's, let's take a look. And we were to count them out, there's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's still C5H12. That counts as an isomer. So now let me show you all the mistakes that students make when drawing this isomer, right? Because then they say, well, what if I did this? So here's the original isomer that we drew. 4 in a row, 1 down. Well, then I see, well, what about this? These are the same thing, okay? Hopefully everyone can see that. These are the same isomers, because if I just take this molecule and flip it, it's the same thing as the first one, which is the same thing as what I have drawn with all the H's in. So these are still the same molecule, okay? Let's do the next ones. I get this a lot. These are all the same molecule. All 4 of these are the exact same thing, just drawn in a different fashion, okay? Well, let's keep drawing it to show you all the variations that I get all the time with this. So here's the next one. Some people say, well, what about this? What about that? Well, all you have to do is take this carbon here and just rotate it down to be over here, right? That would be like me doing this. Well, what about this? This must be different. Well, no, it's still 4 in a row. 1, 2, 3, 4, right? It's hard to see. 4 in a row with one down. All I did was just bend my orientation to make it look different, but I didn't actually reconnect anything into a different fashion. All right, so this, these two, all the same thing. You could even get more extreme and say, well, what about this? Still the same thing, because all I'd have to do is take this one and just rotate it down that way, take this one, rotate it down that way to be straight, and now it's here and here, right? And I'm still at the original. Okay, the same thing with this thing. If I just take this one and rotate it there, now it's going to be over there and it's the original. So this is really, the issue here is really kind of like spatial orientation. These are all the same molecule. So what do you do to make another version? Well, here's the final version. Do the exact same thing that you did to the original. Disconnect one from the main chain and reconnect it somewhere else. So now we're here. So now this is the final version. And the way it's going to look is it's going to look like this. 3 in a row, 1 up, 1 down. If we add all our H's, they're still C5H12. All right. The condensed formulas will be different. So this one, this original one would be that. This next one would be, and I'm going to go left to right. Okay, so this is this carbon right here, because it only has one H directly connected, and then the CH3 goes in parentheses because it's a branch, and then there's your last CH3. And this last one, there's 2 ways of doing it. You could do it like this. So here's carbon 1, and then here's carbon 2. It has no H's directly connected to it, and then here's the branches that are connected. And then here's the final carbon. So that's one way of doing it. Because these branches are 100% identical, the other way of doing it is this. This is the preferred way, because we take these 2 identical branches and just connect them there because of that. And so that's an easy way to do it. It only works if the branches are 100% identical. And then for naming these guys, the naming's a little bit trickier, but let's take a look. Naming them, well, this one's easy. This one's just called pentane. This one's not a pentane anymore. This is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4. Notice the reason I started on this side and not the left is because the branch will be on carbon 2. If I did it the other way and I made this 1, 2, 3, 4, the branch would be on carbon 3. Okay, and the rule says we want the lowest possible numbers we can get. And so obviously if there's a double bond or a triple bond, it gets priority, but there's none here. So then my branch now my branch becomes the next most important thing. And so I want the branch, or at least the first branch, to be on the lowest possible number. So this would be carbon 2. So this is called 2, why did I write a C? Let's fix that. This is called 2-methyl butane, because it has a methyl group, a group of 1 carbon in length, on carbon 2 of the main butane chain. And then this one is going to be, doesn't matter if I number it this way, 1, 2, 3, or if I number it this way, 1, 2, 3, the branches are on carbon 2 either way. So this is going to be called 2, 2 dimethyl propane. So the reason I have 2 numbers is because there's Dimethyl means two groups of one, and then the 2 and the 2 tell me where to find the two groups. They're both on carbon 2, one up, one down. And so that's how we name these. I'm gonna do one more video for drawing isomers, and we'll go to a larger isomer, and hopefully you'll get a little bit more practice with it. But we're gonna cut this video here, and then we'll go to the back of this, which was where we're gonna draw a bigger isomer. And the bigger they are, the more variations they have, or the more isomers they have.